Probability trees is just simply another way of organizing your work. So you can use two-way tables to organize your work, or you can use trees to organize your work. And sometimes things fit more conveniently in a tree than they would in a table. The main use for tables is when you have raw data, like the number of students, the number of bicycles, whatever. We typically use the probability trees when we have the probabilities already figured out for us. Okay? So I know that the probability of winning a certain race is 70% or whatever. Okay? And that's the big one. But you can, of course, they are interchangeable. Okay? Because you can get a probability, then put it into a tree. You can use probabilities on a two-way table as long as you're very careful about the fact that they're probabilities. But usually, these are reserved for when you have the probabilities. So let's just remind ourselves what they look like. Remember that every tree always has a starting point. Then you get branching. So let's say we're playing a game and we could win, lose, or draw, right? So let's say we play our first game. Label it first game. And then you can either win, you can lose, or you can draw, right? Each possibility gets a branch. Okay. Then, let's say you've got to win 2 games. Well, if you can't play just one, so that means we have to play a second game. And we could either win, lose, or draw. If we lost the first one, we could either win, lose, or draw. And then if we drew the first one, it's win, lose, or draw. Looking familiar? Now, if the success is win 2 games, here's a win, here's a win. So from that one, I don't have to branch anymore. Do you see it? I've already satisfied the condition. I'm done. But if I won and then lost, I could still win, lose, or draw again from those. And every one of these others would have 3 more branches. Now, that's a lot of branches, and I'm getting really tight there, so I'm not going to draw them all. But do you see that because we satisfied the condition with only 2 games, we didn't have to play a third for that particular branch? Now, for all the other branches, we still had to play a third. Make sense? Now, what if I said success is winning 2 games, and we've already won 1? Okay? Then I wouldn't need to branch out from this win and play a second game here in this one, because if I've already won 1, this second win in that game means I'm done. Does that make sense? So be careful. This is very unusual that they tell you that you've already have something, but we had one in last year's exam where they were buying milk out of a machine, and the woman already had put in pushed the button and gotten 2 liters of milk, but she wanted 3 liters. So she still had to buy more milk, but you have to consider what she already had. So be careful if you have something already. It's a little bit tricky. Yes, it'll say she already chose once and got 2 liters. Okay. So if she was looking for 3 liters, then she couldn't get another 2-liter bottle, but she could get a 1-liter bottle or a half-liter bottle. If she gets a 1, she doesn't need another, but if she got a half, she still needs another half to win. So again, it's a starting point. So be careful. That can happen to you. All right, let's talk about just the basics of what these things look like and what information you can get from them. So let's say, we're just going to go win, lose. Let's say you have your starting point, right? And the first game, you can either win or lose. Now let's say we're playing a sport and we're particularly good at the sport. So in that case, we have a 70% chance of winning. Okay? If we have a 70% chance of winning, then what chance do we have of losing? 30%. Good. Now remember, when we're finished with these, we're going to have to do some math with these. So can I use percentages to do the math? No, I have to convert them to what? Decimals, which simply means move the decimal 2 places to the left. So that becomes 0.7. And this one would become 0.3. Okay? You have to convert them to decimals in order to do the math. Okay? Now, let's say that if you won the first game, you're more likely to win the second game. So let's say on the second game, your chances of winning are 80%. So we would call that 0.8. What does that mean your chances of losing on the second game are? 20%, which we would convert to 0.2. Excellent. Okay? Now, if that's the case down there, then it also has to be the case here. It can't be different as you go down. Okay? Now, another thing is you need to remember that every set of branches has to add together to make what number? 1. Excellent. Okay? So these 2 branches have to make a 1. These 2 branches have to make a 1. Every set of branches the probabilities have to add to make 1. If they don't, then you've got a problem. Okay? All right. Okay. All right. So, if you go to this first set of branches, we go to win, and then we go to win. So that's a probability of 2 wins. And when you travel along the branches, this one is 0.7, this one's 0.8. To get to the final end, what operation do I use for those? Times. You bet, times. So it's 0.7 times 0.8, which is 0.56. Remember, pardon me?
What's in the bracket after the P?
2W, 2 wins. Sorry, my handwriting. Let me see if I can make it look neater. So it's the probability of 2 wins, if you follow that. Because what's happening is we're saying this is a win and another win. And anytime you have the word and with probability, it always means multiply them together. Okay? So following this branch, first you get to win, then you have lose. So this is a probability of win, then lose. So that means just take those 2. So 0.7 times 0.2 gives you 0.14. Make sense? Then here, it's the probability of lose, then win. So probability of lose, then win. Now those are 2 distinct things because the probabilities are changing as you go. So make sure the order counts. So that's 0.3 times 0.8, which is 0.24. And the last...
When you add the decimals together?
I'm just taking this times this. 3 times 8 is 20.
Wait, and the probability of win lose, does that say 14 or 44?
14.
14.
Because it's 0.7, it's 0.14 times 0.2. And you can remember, you'll have calculators to do these if you get confused about it. So that the probability of the last one is the probability of lose, which is 0.3 times 0.2, which is 0.6. Okay? Now, we also talked about this. All of the ends of these branches, all of these probabilities have to add up to a certain number as well. What number? 1. Okay? Right. What if I want 2 branches? I have 2 branches that satisfy it. Say I want any time where you lose. So here's a loss, and here are 2 losses, right? Now let's just do lose 1. So anytime you lose 1, well, there are 2 different scenarios where you can lose 1, right? And that one is the other possibility. This says this or this. And so think about, what does it mean? What operation does it mean when you have or? You don't multiply them together. What do? We add them together. Okay? So and means multiply them, or means add them. Looking familiar? Okay. So let's just go to Education Perfect and look through some of those sample problems. Again, remember, what you're aiming at is where you need to focus. If you're aiming for achieved, you need to get two pieces out of this right. Merit, that usually means you got to get a third one out of there. Then, of course, excellence means you have to get at least one excellence from each one. So, there's a special teams award presentation at the school assembly. There's no prior warning about the award, but the hockey team is to receive the award. The award must be accepted by the captain, or if the captain is absent, by the vice captain. The captain is present at the assembly 95% of the time. Okay? So, the vice captain is present at the assembly 93% of the time that the captain is present, and 75% of the time if the captain is absent. Okay? Some of the information is shown on the tree below. So here we go. So first of all, the captain is present 95% of the time. So we have captain present. So the first branching is either the captain is present. The captain is present or the captain is absent. Right? Both of those first branches talk about the captain. If he's present 95% of the time. So 0.95. So how much does that mean he's absent? Just subtract it from 1, 0.05. Be careful. Use your calculator. Just do 1 minus the decimal because you don't want to get it in the wrong spot. Okay? Then the next thing is about the vice captain. He's either present or absent, but he can be present or absent if the captain is present. He can also be present or absent if the captain is absent. If the captain is present, it says that the vice captain is there 93% of the time. So what is that as a decimal?
0.93.
There you go. Which means he's absent the other part of that one, which would be 0.07. Okay. If the captain is absent, then the vice captain is absent a little more, and I've forgotten the number, doggone it. Let's see. I don't remember what it was. Say it was 73%. Who cares? So 0.73, which would give the rest of it as 0.27. Right? So they're going to do this. They're going to give you enough information that you need to fill in. Some of them you'll just write in, but then the others you subtract from 1 to get the other value. Look good? Okay, so you're going to have to fill these in on some of them. Now, let's get the answers on there so we can see what kind of credit we'd get. It was 75% of the time. Sorry, I was pretty close. Okay, so there you go. Now, calculate the probability that both the captain and vice captain of the hockey team will be present at the assembly as the award is being presented. So, that probability, the captain is present and the vice captain is present. Okay? So what was that, 0.97 or something? I can't remember. So, it's this one and that one. So that means you will what? Simply multiply those two probabilities together. If you're following a branch all the way across, then you just multiply the probabilities. So you'll see from there working, there's 95% the captain was there, times 93% the co-captain was there, if the captain was there, gives you the probability of both captain and vice captain is 88.35. Now again, remember, in probability, the probability statement is key. If you don't write this business here and you just put the number, it's not correct. You need to write the probability of the captain and vice captain is. Right? So on all probability questions, you answer it with a probability statement. Okay? If you don't, it's not good. Okay? All right. Calculate the probability that the award will be presented to the hockey team at the assembly. In other words, either one or the other has to be present. Right? So, doesn't matter. One of them, at least the captain or the vice captain, is present at the assembly. So all we're going to do is, don't worry about the numbers. We'll talk about that in a second. All we're going to do is look at when that happens. Captain present, that means anything after that is good. Even if the vice captain's not there, we don't care, right? So if he's present, this branch and this branch would both work. Okay? If the captain is absent, the only one that works is when the vice captain is present. Because these two, this branch here, would be where they're both absent, and we can't have that. Right? We need at least one of them to be there. So, all we need to do is find the probability here to here, get one probability, here to here, get that one, and here to there to get that one. Now, what do we do? What operation is it when you're following a branch? Times. But then we got three different ones here. What is it when you have three different ones? What am I going to... be careful. Add. Yeah. Okay? We'll just add them together. Because this is this branch or this branch or this branch would work. And or always indicates addition. Okay? Pretty straightforward. Okay. So you can see what they did. Probability that at least one of them is there. Okay? And they did it slightly different. We can just add them together. If the vice captain of the hockey team is absent from the assembly, there's a 40% chance that he is sick. If the captain is absent, what is the probability that the vice captain will also be absent and not sick? So the vice captain of the hockey team is absent. There is a 40% chance that he is sick. Okay? So, what is the probability that the vice captain will also be absent and he is not sick? So just going back, find all the places vice captain is absent. Vice captain is absent. Right? Oh, wait a minute. But it says something about the captain being present. I hate doing back and forth like these. Okay. Let me see if I can find this with it. Yeah, they've got a tree drawn. Okay. Here we go. Captain is absent. The vice captain is also absent. So we get two more branches because we haven't talked about anything but attendance here. We're talking about both of them being absent and the vice captain is sick. Well, he's sick 40% of the time. He's not sick 60% of the time. So he's not sick. That means we want that branch at the bottom. So we have to go with captain absent, vice captain absent, vice captain not sick. And what do I do with all those numbers traveling along those branches? Multiply them, yeah, times. Okay? All right. So we added another category, which added another branch. But we only were worried about that branch was when he was sick. And if he's sick, he's not there. Or we're only worried about when he's absent. Okay? And also, we only didn't put it onto this one because the question specifically said that the captain was absent as well. Okay? So be very careful in what you're looking with what the question says. Okay? So there's 25% times 60% gives you the final answer. Now, let's look at our grading boundaries. If you get the correct solution on the first one, it's achieved. If you get the probability calculated correctly on the second one, it's achieved. if you calculate the probability for all of them, in other words, you add those up, that's a merit. Okay? And then if you do the more complex one where there's something else, another piece of it, don't worry about their working, just look at their thing. If you get that, that's an excellence. Okay? And that wasn't bad excellence, it's just you had to add one more layer, right?
Can we go this one?
Okay. I beg your pardon? Okay, so go to another one. Let's go to another test. Look at a three-parter. Here we go. Bobik wants to see if the team has an advantage of their school game since they've won twice. The first game is played at school A, the second at school B, the third at school A. From the records, he finds that the probability of either of the team winning at their own school is 3/4, which is the same as 0.75. Easier with a decimal than a fraction. Okay. First game played at school A. Then school A has a 75% chance of winning, or 0.75, which means school B has a 0.25. Right? So you're just plugging in those numbers. Second played at school B. Well, that means it favors school B, so they'll get the 0.75 this time, and school A will get the 0.25. Okay? All right. And then you can just follow the branches. Now, they used fractions. You can use fractions to do that. And so what happens is you're going to get two branches that work. So they found the probability of one branch, the probability of the second one, and then you add those two probabilities together to get the total probability. Okay? And again, they used fractions. You are perfectly happy to use decimals. All right? Okay? Now, if A wins the competition, what's the probability the winner would not be decided until the end of the third game? So what you're doing is you're comparing the probability if A wins to the probability if B wins. We'll look at the working on that one real quickly. Right? So, probability of that A wins, two wins from A. Probability that ABA wins. So there's three things to multiply there. Or BAA gives you another third. Okay? If you find that, that's a merit. When you're comparing those two probabilities, you already have the probability of that thing happening. You just found that 30 over 64. Then the 42 over 64 is when they just played the two games. You're comparing those probabilities. And remember, when we had those probabilities, it's the same as when you're comparing two probabilities, that's like relative risk. And remember, anytime you do that, what happens is, if you have 30 over 64 divided by 42 over 64, remember when you're dividing two fractions, so that's really multiply by the reciprocal, and those 64s will go away every single time, because it's always going to be the same number on the bottom. It's the number of games played, right? So that small piece of comparing those two probabilities okay, and then they want you to explain it, and that is almost 2 times. So you divide it out into a fraction, and divide it out into a decimal, it's 1.9. That tells you that the other team is almost twice as likely to win. Not quite twice as likely, so make sure you say almost. Starting to look familiar? Reminding you of what it looks like? These are fairly straightforward. It's just a matter of knowing what number to put what, and remembering that if you go along a branch, you're always multiplying. If you have more than one branch that makes the statement true, that means you take those probabilities and add them. If you're comparing one probability to another probability, that just means put the first probability on top of the second probability and divide it out. Okay? And you can do that in your calculator and just get a straight decimal. Okay. So I'm going to set this, and you can work on as many as you'd like. Pretend that you've done some.